Hello and welcome to this comprehensive lecture on nuclear magnetic resonance, or NMR, and the fascinating concept of spin quantum numbers. Today, we're going to dive deep into how these principles work, why they matter, and how they're used in science, medicine, and beyond. Let's get started. Let's begin with a simple question. What is NMR? Nuclear magnetic resonance, or NMR, is a scientific technique that allows us to study the magnetic properties of atomic nuclei. But why is that important? Imagine this. Your body, the food you eat, the materials you interact with every day, these are all made of molecules. At the core of these molecules are atomic nuclei. NMR gives us a window into these nuclei, helping us understand the molecular structure and behavior of matter. Take water as an example, a molecule that's essential to life. By using NMR, we can analyze how the nuclei in water molecules respond to magnetic fields. This provides us with critical information about their properties and interactions. Now, think about this. The water in your body, the proteins in your cells, and even the molecules in your breakfast cereal. NMR has the ability to tell us how these molecules are structured. It's like having a superpower that lets us see the invisible world of atoms. But wait, how do these nuclei interact with magnetic fields? What makes them special? That's where the concept of spin comes into play. Spin is a fascinating property of nuclei that plays a key role in NMR. Without spin, NMR wouldn't exist. But don't worry if that sounds a bit abstract. I'm here to break it all down step by step, so stay tuned. Let's take a step back in time to the 1940s, when two brilliant scientists, Felix Bloch and Edward Purcell, made a groundbreaking discovery. They developed the foundational principles of nuclear magnetic resonance, or NMR. For their pioneering work, they were awarded the Nobel Prize in Physics in 1952. But their discovery was more than just a scientific breakthrough. It was a revolution. What they unveiled wasn't just a new way to study molecules. It set the stage for one of the most transformative technologies in modern medicine, magnetic resonance imaging, or MRI. Now let's dig into the core concept behind NMR, the spin quantum number, or I. This is a fundamental property of atomic nuclei and plays a central role in how NMR works. Think of it like this. Just as the Earth spins on its axis, many atomic nuclei also have a property called spin. This spin gives them angular momentum, which is a kind of intrinsic rotation built into the nucleus itself. Here's why spin is so important. The spin quantum number determines whether or not a nucleus can interact with a magnetic field. If I equals 0, the nucleus doesn't spin and won't interact with the field. These nuclei are invisible to NMR. But when I greater than 0, things get interesting. These spinning nuclei create tiny magnetic moments that interact with external magnetic fields. This interaction makes them NMR active, meaning we can detect them using NMR techniques. To put it simply, if a nucleus spins, we can study it with NMR. If it doesn't, it's like a radio that's turned off. We can't pick up its signal. But not all nuclei spin the same way. So, what determines a nucleus's spin quantum number? And how do we predict whether it's 0, half, 1, or higher? Let's find out in the next section. Let's explore how spin quantum numbers are determined. Every atomic nucleus consists of protons and neutrons, and each of these particles has an intrinsic property called spin. Spin is a fundamental quantum property that contributes to the total angular momentum of the nucleus. Protons and neutrons each have a spin value of half. But what determines the spin of the entire nucleus? It's the combination of these individual spins, like adding vectors, to calculate the total spin of the nucleus. Here's the key. If protons or neutrons pair up, their spins cancel each other out. For example, one proton with spin plus half and another with spin minus half will contribute zero net spin to the nucleus. But if there's at least one unpaired proton or neutron, it contributes to the overall spin quantum number of the nucleus. This is why nuclei with odd numbers of protons or neutrons often have non-zero spins, making them NMR active. Think of it like balancing on a seesaw. If everything pairs up perfectly, the seesaw stays level, spin equals zero. But if there's an unpaired particle, it tips the balance, giving the nucleus a measurable spin. So, the spin quantum number I of a nucleus is the vector sum of all the spins of its protons and neutrons. Whether a nucleus is NMR active depends on whether it has a non-zero spin quantum number. Now that we understand how spin arises, let's explore what makes certain nuclei interact with magnetic fields. Why are some nuclei invisible to NMR? Let's find out. Now, let's explore the relationship between atomic structure and spin. The spin quantum number of a nucleus depends on two key factors: the number of protons, also known as the atomic number, and the total number of protons and neutrons, which is the mass number P plus N. Here's the rule. When a nucleus has both an even number of protons and an even number of neutrons, their spins pair up and cancel out. In such cases, the nucleus has no net spin, and the spin quantum number I is zero. These nuclei are NMR inactive. However, if there's at least one unpaired proton or neutron, the nucleus will have a net spin. This results in a non-zero spin quantum number, making the nucleus NMR active. For example, carbon-12 has an even number of protons and neutrons, so its spin quantum number is zero. Hydrogen-1 has one proton, making its spin quantum number I equals 1/2. Nitrogen-14, with an unpaired neutron, has a spin quantum number of I equals 1. So, the atomic and mass numbers dictate the spin quantum number. Even nuclei are silent in NMR, while nuclei with unpaired particles create the signals we study. But spin alone isn't enough. Let's explore how these spin patterns influence the way we detect and interpret NMR signals. Stay tuned. Let's break down the patterns of nuclear spin based on the number of protons and neutrons in a nucleus. This is a key factor in determining whether a nucleus is NMR active. When a nucleus has an even number of protons and an even number of neutrons, their spins pair up and cancel each other. This results in a spin quantum number of I equals 0. For instance, helium-4 has two protons and two neutrons. Since all the spins are paired, the nucleus has no net spin, making it NMR inactive. But what happens if there's an odd number of protons or neutrons? At least one particle remains unpaired, contributing to the total spin quantum number. This results in I greater than 0, making the nucleus NMR active. For example, deuterium has one proton and one neutron. Because the spins don't completely cancel, the nucleus has a total spin of I equals 1. Similarly, hydrogen-1, with just one proton, has a spin of I equals 1/2. So, the spin quantum number depends entirely on how protons and neutrons pair up within the nucleus. Even nuclei are silent in NMR, while odd nuclei create the signals we analyze in spectroscopy. Now that we understand spin patterns, let's explore how these patterns influence the NMR signals we detect and interpret. But spin alone isn't enough. Let's explore how these spin patterns influence the way we detect and interpret NMR signals. Stay tuned. Now, let's take a closer look at some examples of spin quantum numbers. Different nuclei exhibit different spin quantum numbers depending on their structure, and these examples will help us understand their behavior in NMR. First, we have nuclei with zero spin quantum numbers, I equals 0. In these nuclei, all protons and neutrons are paired, and their spins cancel each other out. As a result, there is no net spin, and these nuclei are NMR inactive. A perfect example is helium with mass number 4 and atomic number 2, where both protons and neutrons are paired, leading to I equals 0. Carbon-12 and oxygen-16 are also similar to helium-4 in this regard. Their spins cancel completely, making them invisible in NMR experiments. Next, we have nuclei with integer spin quantum numbers, such as I equals 1. These nuclei typically have an unpaired particle, resulting in a net spin that makes them NMR active. For example, deuterium, an isotope of hydrogen, has one proton and one neutron. Because their spins don't completely cancel, the total spin is I equals 1. Nitrogen-14 with mass number 14 and atomic number 7 is another example. Its total spin quantum number is I equals 1, making it detectable in NMR studies. Finally, we have nuclei with half-integer spin quantum numbers, such as I equals half. These nuclei are among the most commonly studied in NMR due to their simplicity and abundance. Voiceover: hydrogen 1 mass no and atomic no 1, neutron no 0 is a prime example. It has just one proton, giving it a spin quantum number of I equals half. This makes it the most widely studied nucleus in NMR spectroscopy. Voiceover: carbon-13 with mass number 13 and atomic number 7 is another critical example, widely used in organic chemistry for NMR analysis. Its spin quantum number of I equals half makes it perfect for studying molecular structures. To sum up, nuclei can have zero, integer, or half-integer spin quantum numbers, and this determines whether they're detectable in NMR. Understanding these examples helps us interpret NMR signals and analyze molecular structures. Nuclear magnetic resonance, or NMR, works by exploiting the interaction between spinning nuclei and an external magnetic field. But how exactly does this happen? Voiceover: only nuclei with a spin quantum number greater than 0 can interact with an external magnetic field. These nuclei generate tiny magnetic moments due to their spin, allowing them to respond to the field. When placed in a magnetic field, the magnetic moments of nuclei align in specific quantized orientations. For a nucleus with spin quantum no is equal to half, there are two possible alignments: parallel, which corresponds to a low energy state, and antiparallel, which corresponds to a high energy state. This energy difference between the parallel and antiparallel states is critical. It determines the frequency of electromagnetic radiation needed to cause resonance, allowing us to detect the nucleus in NMR experiments. To recap, nuclei with I greater than 0 interact with magnetic fields, aligning in quantized orientations. For I equals half integer, these alignments correspond to distinct energy states, creating the foundation for NMR signals. Now that we understand how nuclei align in a magnetic field, let's explore the core process of nuclear magnetic resonance, the phenomenon of resonance. When a radio frequency pulse is applied, it delivers energy that matches the difference between the two nuclear energy states, parallel and antiparallel. This causes the nuclei to absorb the energy and transition to the higher energy state. This absorption is called resonance. This process works because the RF pulse resonates with the nuclei, flipping their magnetic alignment. Essentially, the nuclei absorb just the right amount of energy needed to switch from the lower energy state to the higher energy state. As the nuclei return to their original lower energy state, they emit the absorbed energy. This emitted energy is detected as an NMR signal, which we analyze to learn about the nuclei and their environment. To put it simply, NMR works like a two-way communication. We send energy to the nuclei using RF pulses, and they send us information back in the form of signals. Nuclear magnetic resonance, or NMR, is an indispensable tool in modern chemistry. Its applications range from determining molecular structures to analyzing reaction dynamics. Let's explore how chemists use NMR in their work. NMR allows chemists to unravel the molecular structure of compounds. By analyzing the magnetic environments of hydrogen and carbon nuclei, we can determine the connectivity of atoms and the geometry of molecules. NMR provides unique insights into bonding patterns by detecting subtle shifts in the magnetic resonance signals of nuclei. These shifts tell us about the chemical environment of each nucleus, whether it's bonded to an electronegative atom, part of a ring structure, or involved in resonance. Another powerful application of NMR is studying reaction dynamics. Chemists can use NMR to monitor how molecules change during a reaction, identify intermediates, and determine reaction rates. The most commonly used forms of NMR in chemistry are proton NMR and carbon-13 NMR. Proton NMR focuses on hydrogen nuclei and is widely used because of 180 degrees Celsius hydrogen's abundance in organic compounds. Carbon-13, on the other hand, provides detailed information about carbon skeletons, making it invaluable for structural analysis. In summary, NMR is a cornerstone technique in chemistry, providing unmatched detail about molecular structures and dynamics. It's a chemist's go-to tool for understanding the invisible world of molecules. Nuclear magnetic resonance, or NMR, is not just a tool for chemistry, it plays a vital role in biology as well. By using NMR, scientists can study the structures of complex biomolecules and gain insights into how they function. NMR is particularly powerful for studying biomolecules like proteins, DNA, and RNA. It allows us to determine their structures at an atomic level, providing a detailed understanding of their shapes and how they fold. But NMR doesn't stop at structure. It also reveals how molecules interact with each other. For example, by observing subtle changes in the NMR signal, scientists can map out how a protein binds to DNA or how a drug interacts with its target molecule. NMR is also a unique tool for studying molecular conformations and dynamics. It provides information on how biomolecules change shape, interact, and function under different conditions, offering insights that are critical for understanding biological processes. In summary, NMR is a cornerstone technique in molecular biology. It provides unmatched insights into the structures, interactions, and dynamics of biomolecules, helping us unravel the mysteries of life at the atomic level. In medicine, nuclear magnetic resonance has revolutionized diagnostics through the development of magnetic resonance imaging, or MRI. Let's explore how this life-saving technology works and its impact on healthcare. MRI is one of the most widely used applications of NMR. This advanced imaging technique uses the principles of nuclear magnetic resonance to visualize structures inside the human body. The key to MRI is the hydrogen nuclei, found in water and fat molecules in the body. These nuclei interact with magnetic fields and radio frequency pulses to generate signals that form the basis of MRI images. One of the greatest strengths of MRI is its ability to provide high-resolution, non-invasive images of soft tissues. It's particularly valuable for diagnosing conditions in the brain, spine, muscles, and joints. MRI has become indispensable in modern medicine, from identifying brain tumors to detecting spinal injuries and monitoring joint health. MRI provides crucial insights without the risks of radiation exposure. In summary, MRI is a direct application of NMR technology that has transformed how we diagnose and treat medical conditions. It's a powerful example of science improving lives. Nuclear magnetic resonance, or NMR, is not just a tool for chemistry and medicine. It also plays a crucial role in physics. Let's explore how NMR provides deep insights into the fundamental properties of nuclei. One of the key applications of NMR in physics is studying nuclear spin behaviors. By observing how nuclei align and transition between spin states in a magnetic field, physicists can explore the quantum mechanical properties of matter. NMR also provides precise measurements of nuclear magnetic moments. These moments reflect the distribution of charge and spin within a nucleus, offering insights into its internal structure and quantum properties. NMR enables physicists to study nuclear interactions in detail, such as how neighboring nuclei influence each other. These interactions are crucial for understanding complex phenomena like magnetic coupling and the behavior of condensed matter. In summary, NMR is a powerful tool in physics, unlocking the secrets of nuclear properties and interactions. Its ability to probe the quantum world makes it indispensable for advancing our understanding of matter. From unraveling the mysteries of nuclei to revolutionizing healthcare and molecular science, NMR is a cornerstone of modern research. Let's conclude with the key takeaways from this journey through NMR's world. Let's wrap up with the key takeaways about nuclear magnetic resonance, or NMR. This powerful technology has revolutionized science and medicine in multiple ways. NMR is a non-invasive, versatile tool that allows scientists to study both molecular and nuclear properties with incredible precision. It's not just a research tool. NMR underpins essential technologies like magnetic resonance imaging, which provides life-saving diagnostics in healthcare. From unraveling the structure of molecules to diagnosing diseases, NMR continues to shape the world of science and improve lives. Its versatility and impact make it a modern research and technology cornerstone. In conclusion, nuclear magnetic resonance, or NMR, reveals molecular and nuclear details based on the fundamental property of spin. By leveraging this phenomenon, we gain insights into the intricate structure of matter. The applications of NMR extend across disciplines, from exploring fundamental scientific questions to driving innovations in healthcare, physics, and beyond. It's a cornerstone of both fundamental and applied sciences. Thank you for joining this journey through the fascinating world of NMR. Its versatility and impact remind us of the endless possibilities science offers to explore and innovate.